All right, so that rabbit problem brought in the idea of doubling time, which is just, like I said, the amount of time it takes for the population to double from the initial population to twice that. So we can solve this kind of generically, solve for the doubling time, which will usually get called capital T, so long as we know the growth rate, K, right? Just like we did with the rabbits. So you start with P0 population, you want to grow to twice that, and that's happening in some amount of time, capital T. And so we can solve this. Of course, we're going to divide both sides by P0. Then we're going to take the log of both sides, and since we've got E here, we're going to use natural log. And remember, ln of E is 1. And then we just divide both sides by K. We get, so our doubling time is ln2 over K. And the nice thing is that since this book sets it up as decay being either negative KT, then this is the exact same formula for half-life, which is the amount of time for a decaying function to go from the initial population to half the initial population. But we'll talk about that later. Okay, so this is kind of similar to some of the book homework problems. We have a population growing at a constant annual growth rate of 30% per year from an initial population of 100. So this is not continuous growth, this is constant growth rate. So this is like at the end of the year, 30% more people magically materialize in the town. Right, and so in that case, we are using an A, B to the T model. Our initial population is the A, right? So we've got 100, and the question is, what is B? And this is like what we had in 6.1 when we talked about compound interest, right? If we're growing 30% per year, that's like multiplying the population by 1.30 every year. So our B is just going to be 1.30, you don't need the 0 on there, to the T. Okay, so there's our exponential formula. Now, we can convert this to a continuous growth rate formula by basically saying, okay, I want this to be e to the kt, but I remember raise a power to a power, you multiply the powers, right? So I can think of this as e to the k to the t. So then that means we're really only interested in this part, right? Because everything else is the same between the two formulas. So we have our b of 1.3 that we want to be expressed as e to the k. And we just need to find, hey, what is that k? Well, we're going to do that. We're going to take the log of both sides. So we've got k ln of e, right? So which is 1. So we've got our k right there. So we know what our k is. So now we can say, okay, great. This is 100 e to the ln 1.30 times t. So we're usually going to put the t out front, but I'm going to have to move it all over. So t ln of 1.3. And there's our continuous growth rate. So really, when you need to convert from a constant growth rate to a continuous growth rate, you are solving b equals e to the k, and you're solving that for k. Pretty straightforward there. All right, so this is definitely a homework problem. All right, so in this problem, we have a population increasing from 22,000 to 27,000 over 5 years at a constant annual percent growth rate. So the total percent increase in population, this is something you would have learned way back in elementary school or something. So we have the new population minus the old population over the old population. So this is 5,000 over 22,000, and we've got to go put that in a calculator to see what that is. 5 over 22, so it's 22.73%. Total. Now, the constant percent rate of growth each year. So here, we're actually doing something we did from 6.1, where we've got to find the equation through the 2 points, right? At year 0, you had 22,000 people. In year 5, we had 27,000 people, and we want to fit an A, B to the T model. Now we know what A is, right? Because that's when the input is equal to 0. So we have 22,000 initial population. And so we can look at our ratios, right? We can say 27,000 over 22,000 is AB to the 5 over AB to the 0, right? A's are going to cancel, and so I've got B to the 5th is this 27 over 22. So my B is going to be the 5th root of that, 27 over 22. So exactly for the model, we are looking at 22,000 times the 5th root of 27 over 22 to the T, but we want to know what kind of number that is, right? So we've got 27 over 22 all raised to the 1/5. There we go. So our B value, 1.0418. That's good enough. 0418. Okay. So roughly 1.0418. So our constant percent rate of growth each year is going to be the decimal part of that. So we're looking at 4.18% growth. All right. Now, of course, that's not what this third question is. That would be the equation for it, right? So this is the formula. So, but we need to, if we want to find the continuous annual growth rate, we need the 5th root of 27 over 22 to equal e to the k, right? That's our b equals e to the k. We're going to take the natural log of both sides. So ln of that lovely number, 27 over 22, is equal to k. That we definitely need to go look up. So we are going to take the natural log of 27 over 22 to the 1/5 power, which GeoGebra called g. So we are looking at 0.04096. So 0.04096. So about 4.096%. It's all, the continuous growth rate is always a little bit less than the constant growth rate. So there we go. And we're going to stop there and go to the next video.